Hello everyone, welcome you all to the next session on relations and functions of class 12 mathematics. In this session, we'll solve a few more problems from miscellaneous exercise. Here is a fourth problem. Show that the function f from R to the set containing the element x belongs to R such that x lying between -1 to +1 defined by f of x is equal to x by 1 plus mod x, where x belongs to R is 1 to 1 and onto function. We have to prove f of x, which is defined here, is a 1 to 1 and onto function. Here the domain is your set of real numbers, whereas codomain is also a set of real numbers, but not all the real numbers. It contains real numbers from -1 to 1. That is, excluding -1 and +1, you have all the real numbers between -1 and +1. This is your codomain. And the function is defined as f of x is equal to x by 1 plus modulus x. Now let's see how to prove this function is 1 to 1 and onto. Now we have modulus x in your f of x in the denominator. So to have a better understanding of how to go for 1 to 1 and onto, let us try to understand what is our modulus function. Now the definition of modulus function is, that is, mod x can be defined in two ways. One is it can be positive when your x is greater than or equal to 0, and mod x will take negative x when your x is less than 0. So there are two cases for the modulus x. One is positive and one is negative. Now whenever we discuss about anything like 1 to 1 or onto, whatever it is, we need to check for both the cases wherever we have modulus. Let's get into the proof now. First thing, let's start proving for 1 to 1. To have a function to be 1 to 1, we'll take two elements, that is, two distinct elements from our codomain, and we will prove that there are two distinct images or pre-images in a domain. That is, we'll assume our f of x is equal to f of y, and we'll try to prove x is equal to y. If that is the case, we'll conclude that f is 1 to 1. Same way, we'll assume two values, say f of x and f of y. That is, f of x is equal to f of y, where x and y belongs to R, that is, set of real numbers. Now when we have f of x equal to f of y, this implies x by 1 plus mod x equal to y by 1 plus modulus y. Now we have mod x and mod y. We have two things to be considered. One is modulus x and one is modulus y. But whenever we consider any modulus, we have two cases to be considered. One is positive of the input and also negative of the input. Now there are x, mod x and mod y. We have two cases in both the cases. So we'll be having 4 cases where we have to check for your 1 to 1. Let's start from the positive and negative. That is, when we'll assume our x is positive and y is negative. Let's check what happens when our x is positive and y is negative. Will we be able to get an equation or get a relation, say x and y are equal? Let's check. Now what happens when your x is positive and y is negative? When your x is positive, we know modulus x takes the positive value. So you can see here 1 plus x. But when your y is negative, modulus y will be taking minus y. So x by 1 plus mod x equal to y by 1 plus mod y will give us x by 1 plus x equal to y by 1 minus y. Now let's go for the simplification. When we have such an equation, say x by 1 plus x equal to y by 1 plus y, the next thing that we do here is cross multiplication. So here is the cross multiplication process that gives you x into 1 minus y equal to y into 1 plus x, which gives us 2xy equal to x minus y. I'll show you how it is. We'll have x minus xy equal to y plus xy. So when you bring this y to the other side and this xy to this side, you will have x minus y is equal to 2xy. Or you can write it as 2xy equal to x minus y. Now let's discuss the cases that we have. We know x is positive and y is negative. So when x is positive and y is negative, obviously x is greater than y. So that is how we get this inequality. X is greater than y. Now when x is greater than y, it means x minus y is greater than 0. So we have got x minus y is greater than 0. That is, if you consider this equation, that is 2xy is equal to x minus y, we see that the right side is greater than 0. Now let's check for the left hand side. Left hand side is 2 into x into y. 2 is positive, we know that. X is positive, we know that. Y is negative. So positive into negative gives us a negative value. So 2xy is less than 0. That is, your LHS is less than 0, where your RHS is greater than 0. But this is not possible. This cannot be possible. This means that 2xy is not equal to x minus y. Now this is mainly because your assumption that x is positive and y is negative. So when you take two elements, your one positive and other negative is not possible. So we can say like this case is ruled out. Now let's check for x negative and y positive. You'll have a similar argument here. When your x is negative, your f of x becomes x by 1 minus x. When your y is positive, again f of y becomes y by 1 plus y. Again, by the cross multiplication process, we see the same thing. That is, we get it here as 2xy equal to y minus x. Again, our x is negative and y is positive. This means that our y is greater than x. When our y is greater than x, we know y minus x is greater than 0. That is, in the equation that we have got in this case, has the right side is greater than 0. Now, what about our left side? We know 2 positive, x is negative, y is positive. So obviously the left side should be less than 0, because positive into positive gives you negative value. You can have the left side less than 0 but right side greater than 0, but we have both are equal. Hence this is not possible. That is, having one number negative and another number positive is not possible. So you cannot have such cases. Now let's check for both negative and also both positive. Now when we check for both positive, it means f of x and f of y, where x and y are positive, will give you x by 1 plus x is equal to y by 1 plus y. Now again, when you do the cross multiplication, you can see you will have x is equal to y. This means that when both x and y are positive, if you choose f of x and f of y are equal, you get x and y are equal. Similarly, when both x and y are negative, you can see the same process here, and that also gives you x equal to y. So we see that f of x equal to f of y for any x and y belongs to the set of real numbers gives you x and y are equal. This means that f is 1 to 1. So we are done with 1 to 1. The next thing that we have to prove is onto. Now, to prove f is onto, we need to look for an element in the domain set, for which, as usual, I am going to have a diagrammatic representation here. That is, I am going to choose a set. I am going to give a set here like in the diagrammatic form. This is, first is the set of all real numbers, even second one is also a set of real numbers, whereas first one will have all real numbers. There is a second one, that is the codomain, will have real numbers where your elements will be between minus 1 to 1. As I can put it like minus 1 less than y less than 1. Now, if at all I give an input, say x, and if that x is greater than or equal to 0, this takes the output, this gives the output as 1x by 1 plus x. And if my x, for the same x, or if it is less than 0, the output that I'll have is x by 1 minus x. So this is what I have put it in this explanation here. When your x is positive, your f of x takes x by 1 plus x. When your x is negative, f of x takes x by 1 minus x. Now we see that for every value in the domain set, we are able to find a value in the codomain. Now let's say we have an element called y in this codomain. Now what will this be mapped to? So what kind of element we can find in the domain set? So that's what I'm trying to find out here. For which, let me assume this is y, which is nothing but our f of x. So our f of x is equal to y. Having that in the condition, Of course, we have two cases for x here. One is x can be positive and other one is x is less than 0. Now what if our x is greater than or equal to 0? When x is greater than 0, again we'll have our y is equal to f of x. But when your x is greater than or equal to 0, or f of x takes the value x by 1 plus x. So we have y equal to x by 1 plus x. Now when we do the cross multiplication, we have y into 1 plus x equal to x. This gives you y plus xy equal to x. That is xy minus x equal to, or I'll put it in the other way. I can have it as x minus xy is equal to y. That is x into 1 minus y is equal to y. So from this we can get x equal to y by 1 minus y. So when x is positive, we get the value of x as y by 1 minus y. Of course, we have other case here. What happens when x is negative? Now when x is negative, as usual, we'll have y is equal to f of x. But f of x takes the value x by 1 minus x. Again, by cross multiplication and then simplification, we can see x equal to y by 1 plus y. So this means that for two values of x, you will be getting different values here. That is, when you give y as the for any element y in your codomain, we are able to find two elements for two cases. That one is x is positive and other one is x is negative. So the two elements in the domain set are nothing but y by 1 minus y, and the other one is y by 1 plus y. Of course, this is also an element in the set. So when we have y, y is mapped to two elements, as we have two elements for our x, like when x is positive and x is negative. So we see that there is an element called y by 1 minus y, or other element y by 1 plus y in your domain set. Now let's check. This is our x, for which we'll be getting f of x is equal to y. Now to consolidate, I am listing out here, when your x is positive, we have x value as y by 1 minus y, whereas f of x is x by 1 plus x. Now again, when x is negative, our x takes the value y by 1 plus y, whereas f of x takes the value x by 1 minus x. Now with this understanding, we'll try to find out what is the value of f of x when x is positive or negative. Now when x is positive, we'll say f of x. f of x is equal to x value of x is y by 1 minus y. So I substitute x as y by 1 minus y here. As we know, when x is positive, f of x takes the value x by 1 plus x. That is, when your input is x, your output is x in the numerator by 1 plus x in the denominator. That is, your input plus 1 is the denominator. Now, instead of x, we have y by 1 minus y. So, let's see what are we going to get it. When we have f of y by 1 minus y, the input is y by 1 minus y. So, let's have the input as such in the numerator. That is, y by 1 minus y will be in the numerator. And denominator, I'll have 1 plus of the input. So, 1 plus y by 1 minus y. This is how we get this part. And then remaining is all simplification. That is, we'll have y by 1 minus y in the numerator, whereas denominator will have 1 minus y plus y, the whole divided by 1 minus y. So on simplification, we can see that it gives you y by 1, that is equal to y. So we see f of x equal to y when your x is positive. Similarly, you can prove it when x is less than 0. Again, when x is less than 0, your x takes the value y by 1 plus y. When your input of f, that is f of x, is equal to x by 1 minus x when your x is less than 0. So when your input is x, your output is going to be x in the numerator by 1 minus x in the denominator. Now in the place of x, we have y by 1 plus y. So this gives us y by 1 plus y in the numerator, whole divided by 1 minus of y by 1 plus y in the denominator. Now simplification, as usual, we have to proceed with, and we can see that gives you the value y, that is f of x is equal to y. So we see that f of x is equal to y when your x is positive and also x is negative. So for all the cases, we are able to find f of x equal to y. That is, for every element y in the codomain set, we are able to find a pre-image in your domain set. So this means that there exists some value called x equal to y by 1 minus y and y by 1 plus y, which is where this x and x is an element in R, such that f of x equal to y. So this tells you that f is onto. So we have proved there is a pre-image for every element in the codomain. So we have proved f is onto. That's what we have. We have to prove f is 1 to 1 and onto, and we are done with 1 to 1 and onto. Keep it in mind that whenever you have modulus, you need to check for both the cases. One is positive and other one is negative. And when you have two elements, when you will be listing out all the combinations. So that's what we have done in this problem, and we have concluded, we have showed that the given function is 1 to 1 and onto. Let's move on to the next problem. The problem next we have is 8th problem. Given a non-empty set X, consider P of X, which is the set of all subsets of X. Define the relation R in P of X as follows. For subsets A, B in P of X, A are B. This means that A is related to B if and only if A is a subset of B. Is R an equivalence relation on P of X? Justify your answer. So ultimately we have to check whether the relation R that is defined here is an equivalence relation on P of X or not. Now let's get back to the question once again. We have a non-empty set X and a set P of X, which is nothing but set of all subsets of X. So P of X is a set of all subsets of X, and there is a relation in P of X. That is, if at all you take any two sets in P of X, those two elements are related. That is, those two sets are related if and only if the first element is a subset of the second element. That is, first set is a subset of the second set. So this is how the relation has been defined, and we are supposed to check that the given relation is an equivalence relation or not. Let's start writing what is given here. Instead of writing all X and P of X, let's make it short by writing only the relation, that is representing the relation as a set. Now the relation R is nothing but set containing the ordered pair, that is A comma B. There is this A is an element in P of X and this B is also element in P of X. But when you take an element in R, it is an ordered pair A comma B, where A and B are sets and A is a subset of B. So if at all you choose A comma B, it means A is a subset of B. Now we have to check whether this is a equivalence relation or not. I hope you remember, to check a relation is an equivalence relation, we need to check whether that is reflexive, symmetric and transitive or not. Let's start checking whether it is reflexive or not. Now every set is a subset of itself, so that we know that A is a subset of A itself, or B. If you take B, B is also a subset of B. Let me take a set A and I can say that A is subset of A. This means that the ordered pair A comma A is an element of the relation, that is R. So when I'm able to find an element, say A comma A in R, this means that R is reflexive. Here R is not the set of real numbers, here R represents a set of relations. So we have proved R is reflexive. Now let's see whether this R is symmetric or not, for which let me take an element called AB, that is the ordered pair AB belongs to the relation R. Now if at all there is an element AB in R, it means that A is a subset of B. So AB belongs to R implies A subset of B. Now when we say A subset of B, the converse is not true. That is, B subset of A is not possible. So B is not a subset of A. This means that B comma A is not an element in R. So we have an element called A comma B in R, but we are not able to find an element B comma A in R. So this means that R is not symmetric. Let's move on to check whether it is transitive or not. Now to check for transitive, let me take two elements in the relation. That is, one is A comma B and other one is B comma C. Now when I take A comma B, there is ordered pair AB, it means A subset of B, and the ordered pair BC means B subset of C. So this means that we have A subset of B and B subset of C. When I put it together, I can see A subset of B subset of C, which in turn implies that A subset of C. So I have A subset of C. It means that the ordered pair A comma C is an element in R. Hence, we can conclude R is transitive. So we have got R is reflexive and transitive but not symmetric. Hence, I cannot say R is an equivalence relation. So I am concluding here that R is not an equivalence relation. So I was asked to check whether the relation defined is equivalence or not. I could see it is not an equivalence relation. Now we have one more problem in this session. Here is it. Here it is. The 10th problem of the exercise. Find the number of all onto functions from the set containing elements 1, 2, 3 and so on up to n to itself. That is function f from the set containing 1 to n to the set containing 1 to n. We need to find out how many onto functions are possible. Now let's define, give a name for the function. Let me say f. That is, f is a function from the set containing elements 1 to n to the set containing 1 to n. Now this is a given function. Now I need to check how many onto functions are possible in this case. Now we have n elements in both the sets. Let me start with 2 elements and try to find out how many onto functions are here. And I'll try to expand it and then conclude with that. So to have a start with, let me consider f from the set containing 1, 2 to the set containing 1, 2. Now, if at all f should be onto, every element in this set, that is in the codomain set, should have a pre-image in the previous set, that is in the domain set, and it should be unique. So I need to find out all the pre-images of the elements in codomain. Now, instead of writing it as a normal text, it's comfortable, it'll be easy for you if I put it in the diagrammatic manner. So here I have represented the mappings by the diagrams here. You can see the diagram here. So this is the first set. I'll mark it as D, there is nothing but the domain set, and here I'll mark it as C, which is nothing but our codomain. So I have the elements in domain as 1 and 2, even in codomain I have elements as 1 and 2. Same way I have the other combination here. Let me see what are the different combinations I can have. One is mapped to f. So 1 to 1 and 2 to 2 is one way of having a unique pre-image. That is, the element 1 in C has a pre-image 1 and the element 2 in C has a pre-image 2 in D. So there is no repetitions or no similar pre-images here. All are distinct here. Similarly, if at all I choose the other one, there is other way of also representing it. The element 1 in the domain can have 2 as a image. Similarly, the number 2 in the domain can have 1 as a image. Or in the other way, the elements 1 and 2 in the codomain can have pre-images as 2 and 1. So these are the only possibilities of the function that I can have it here. There are no other options to have the representation. Now when I check it, there are 2 ways. This is first way and this is the second way. I don't find any other way to have represented onto function between the sets 1 and 2 and the other set 1, 2. So here the number of onto functions for the given function is nothing but 2. I'll put it as 2 into 1 for the easy reference. Now let me extend this to a set containing 3 elements. That is, if at all we have a set containing set f, from the set containing elements 1, 2, 3 to the set containing elements 1, 2, 3. Now I have 3 elements in the first set and here also I have 3 elements here. Now in this case, let me check how many mappings are possible. You can see all the 6 mappings are listed out here. This is the first mapping and this is the second one. This is third one. I'll call this as fourth. This is fifth and this one is the sixth one. Now look at the first one. You can see all 1 is mapped to 1, 2 is mapped to 2 and 3 is mapped to 3. So this is one way of representing onto function, and the second one has 1 mapped to 1, 2 mapped to 3, whereas 3 mapped to 2. And you can see all other combinations and you can easily check none of the combinations are repeated here. So here you could see 6 different functions for which I can have the same f can be onto. Now I'll give you a minute to go through the remaining combinations. You can see in third one, 1 to 2, 2 to 1, 3 to 3, The fourth one, 1 to 2, 2 to 3, 3 to 1. Fifth one, 1 to 3, 2 to 1, 3 to 2. Whereas in the sixth one, 1 to 3, 2 to 2, 3 to 1. So I have listed out all possible mappings so that the function becomes onto. I don't find any other combination. So I have listed out all the combinations and it comes around 6. Now here is the conclusion, like how am I going to conclude how many onto functions are possible. Now we can check in this case we have 6 onto functions are possible. That is, I can expand the 6 as 3 into 2 into 1. Where does the 3 comes from? 3 is nothing but number of elements in both the sets. You can see in this set here we have 3 elements here. We have 3 elements here, and in the previous set you can see we have 2 elements here. So when we had 2 elements, we represented by 2 into 1. That is why we get it as 2. Now when we have 3 elements, we are representing the number of onto functions as 3 into 2 into 1. So it means like the product is you are multiplying the number 3 with 1 less than that and with 1 less than that. You can see this is nothing but your permutation which you have already learnt. This is nothing but your 3 factorial. Now let us extend this for the number of elements, where number of elements is n. So we have n elements in this set and also n elements in this set. So this tells me that number of onto functions for the given function could be n into n minus 1 into n minus 2, and it goes to 1. This means that it is nothing but our n factorial. So there are n factorial number of onto functions for the function that is defined in the question, that is from the set containing elements 1 to n to the set containing elements 1 to n. So I hope you understood how to find the number of onto functions, and you can extend this for any number of elements. It depends upon the number of elements, provided both the sets, that is the domain set and codomain set, should have equal number of elements. Well, even this case is possible. So we are at the end of this session. So with this I conclude this session with a few homework problems for you. The homework for the day is examples 41 and 47 and exercise 11 and 15. So try out these problems. I'll meet you in the next session with some more problems of the same exercise. Thank you.